Hello there, my name is Jonas Salame. I'm from VIT University. I'm going to discuss B+3 data structure. The topic I'm going to discuss in this video are a definition of B+3, property of B+3, biasing of B+3, those are right biasing and left biasing, how it can look like, and operations in B+3, those are insertion, deletion, and searching of in B+3 and their algorithms, and some advantage and disadvantage of B+3 at the last as well. What is B+3? B+3 is data structure, and it is an M array tree in which all nodes have multiple children. So we can have in B+3 three main components. Those are roots and internal nodes and leaf nodes. So these main three components will be played a great role in B+3. So we'll discuss later on about them. B+3 is an extension of B3 with some rules, such as B+3 will have a keys that represent the leaf nodes. Only keys are present in a leaf node that represent the data pointer or index to the database. So every leaf is connected as a linked list that is at the leaf node. All keys are connected by linked list that makes a dense index. In non-leaf nodes, duplicate may be present, which means that all the keys value are present in the leaf node. So as well, at the parent and root nodes, we can have some copy of root nodes in the root node and internal nodes. So no record is pointer to non-leaf nodes. Non-leaf nodes like root nodes and internal nodes cannot point to the data. Only the leaf nodes will point to the data, point to the record. So in B+3, the data is stored only in leaf node, and internal nodes of B+3 stores only pointers to the child or the block. These internal nodes pointer to the next child, left child, or right child. That pointer only have in B+3. This is a B3. So this B3 will have a pointer to the block and pointer to the data as well, pointer to the record. It is pointer to the record. So this root node, this key value can point to the child, left child, and one right child, and one to the data records as well. At the leaf node, all the key values will point to the data record. So this one points to the data record 2, 3, 4, 5, 7, 8, 12, and 14 will point to the data record. So those are pointers or key values that point to data table. So as we see here, key values are not arranged in sorted order. So these are mixed up from the leaves and the root node. So from B3 you can have a B+3, so it is extension of B3, that is balanced tree. So a special case in B+3 we see that all the leaf nodes are connected by a linked list like this. All leaves are also sorted from lower value to higher number, like ascending order you can say. So here we see the root nodes have a copy of leaf node. This leaf node is present at the root here, and this right leaf node 6 is present at here root node, and this 10 is also present at the leaf node. So in B+3 we have a copy of keys, but here we see we don't have any copy of the key. So this is a special case that we have in B+3. As well here you see we cannot have a pointer to records from the root. Only the data at only the key values at the leaf node can point to the data records. This is a special case we have in B+3. B+3 is a generalization of binary search tree. We know binary search tree, all the left childs have strictly lower than the root node, and the right childs will have strictly greater than the root node. But here we see B+3 seems like that, but we have multiple children, like for example this root node have 4 children here. You see 4 children, but in binary search tree only we have maximum of 2 children. So it is multiple child binary search tree, we can say like that also. This is an example of B+3. We see 1 up to 7 we can form a B plus 3. So here we have 3 children of one root. The root is containing a key value of 3 and 5. At the lower of left child of 3, we can have some less values like 1 and 2. That is strictly lower than the root 3. And here 5 also we can have this copy of 3 is also present at the leaf node, and also right node of 5 is also there. So it can be right biased B plus 3. We will see it later how it comes. And key principles applied over this B plus 3 graph. Here we see order of M, which means we can have maximum of 4 children, order of M, maximum of 4 children, and the minimum of ceiling of 4 by 2 is equals to 2, which is 4, maximum number of 4. So 4 children can be possible, and minimum children 4 by 2, which is equals to 2. Minimum children can this node one have only 2 children, like binary search tree. And maximum key value, which is equals to 3 key value, because this node will point another children, so another block that contains some values that's greater than to the root node. So this, for example, we can have 3 spaces. Those 3 spaces contain maybe 1 key value or 2 key value or 3 key values. That's very much possible, and that is to say that maximum of 3 keys can be possible. Here 3 are filled, and here 2 keys are filled, 1 space is left. We can add 1 more value here, and we can add 1 more value here also. So minimum key value ceiling of 4 by 2 minus 1, which is 1. So a key value means those are pointing, those values that pointing to the data records are called key values. Those key value can be 1. For example, if we remove this 4, we delete 4, we can left with 3. So that's very much possible in B plus 3. So every node will not have a record pointer. Every node means that this root is a node also, and these leaves are also nodes. So those all key values nodes will not point to the data records. Only the leaf nodes will point to the data record. That is what it means. Here are B plus 3 operations. So those are searching, inserting, and deletion operations. Here we are going to see from the scratch how we can create a B plus 3 and insert new key values after creating the B plus 3. So we will see all together in the same example. So here the order is given for order of B plus 3, as B plus 3 is MOI array 3. So order is given in this case is 4. Maximum children we can have 4 here. Minimum children we can have ceiling of M by 2, 4 by 2, which is equals to 2 number of minimum children we can have in one block, and one root node or one internal node we can have 2 number of children minimum. That's maximum key value M minus 1 is equal to 3 maximum key values we can have in one block in one child. So minimum number of keys M by 2, the ceiling of M by 2 minus 1, which is equals to 1. So minimum 1 key value can be present in the node or block. So B plus 3 need to be created from the leaf node to root node. So we'll grow up from creating the the leaf node, and then splitting them and getting the root node. So that is the way we are going to create B plus 3. This algorithm will follow 3 main algorithms are there, 3 cases. In short, it is in short as I formed a note. And if we have a free space in the leaf node, we can directly simply insert the new key at the leaf node. And if the leaf nodes are full, we will split the leaf node and getting a new sibling leaf nodes and getting one more up root node. So that will follow right biasing or left biasing. If we consider all the left child of the root node will be strictly less than the root node, the root value or the root key value, that will be right biasing, because the copy of root node will be added with the right child of the block or the B plus 3. So case number 3, if we have full number of full keys in the leaf node and full keys in the root node, we will split both of them. So that will grow the height of B plus 3. So if also we can have more full indexes in higher level, so we'll continue splitting the index pages. Here is example. So we can read from left to right. So at first we can have 3 block spaces. It is an array. So we can have 3 spaces. We can insert 3 key values in this block, in this child. So this will can have 4 number of children. That's possible in this case because we have order of m. So m order can have m type m number of children. So multiple children is possible. So first inserting 32 at the first place of this array, and next 34, that is ascending order. So we don't need to rearrange these key values. Directly you can insert and scanning 37, and you can add to the last space of this array. So this array is getting maximum of key value that we can enter m-1, number of maximum key values you can insert in b+3. So this reaches the maximum value. So if we want to add more value like 40, we scan 40 and we want to add this key value. So we need to split and getting one more root node. For that we will divide this middle value and we will get right child and left child because m/2 number of minimum child is possible in b+3. So we'll get one right child and one left child. So we will have one root node. That root node will contain this 37 because we are working on right biasing. So the copy of the root node will be present at the right child of the b+3. So here's how it look like, and this is a root node, newly formed root node, and this leaf node that we can get here. So 40 can be added next to 37 because 40 is greater than 37. So all the values, all the key values are present in the leaf node, and leaf nodes are linked by this linked array arrow. Sorry. So next we scan 47, and 47 is greater than 30. We will go down to the right child and add next to 40 because 47 is greater than 40. So we have a space here. We can directly insert this simple case. So we'll insert here. So how we can insert is also we are discussing here. Scanning 51 is scanned here, and 51 will be right to 37 because greater than 37, and it will go next to 47. But here also we reached the maximum number of m-1, maximum number of keys we can insert in one block, one child block. So this block only contains 3 number of keys, so we cannot add 51 directly here. So we have to split this key value into 2 child. So we can form 3 child at the leaf node, and this 47 will go up to the root node. So root node will have space, so 47 will go up here, and it will be written here. That is why. So copy of 47 will come here, and this 51 previously inserted value, this newly inserted value will be added here. Next we can insert 61 also. So 61 is greater than 51. So we will have space here. 61 will be inserted here. So 3 children and 1 root node is with 2 key value will be created by inserting this match value. So all copy of root node will be present at the leaf node, as you can see here. And we can scan also 55 from the given array. After scanning 55 will search where is it is 55. It is greater than 47. We'll go to the right. So 55 is greater than 51 and less than 61. So 55 will be here. 55. But maximum number of key value is filled, so overflow will come. So for that we need to split this block into 2 child. So this 2 child is formed because of this block is exceeding the maximum limit of possible key value. So 55 will go up because we have a space here. 55, the middle value of right child. Next immediate right child will be minimum value of the right child will go to the root node, and this 47 and 51 will be left of, this child, next sibling child of 55. So left of 55 will be 47 and 51, right of 55 will be 55 and 61. Now scanning 49, scanning from, 47 greater than 47, so next to 47 we'll go down here, and we have a space here, you see, and it is greater than 47, so we're coming like this direction, and now it is, the place is here, greater than 47 and less than 51. So this we have a space here. We will rearrange this value by ascending order. You can sort by linear search, linear sort. So 51 will come here, 51 will come here, this place, and this will be filled by 49 new inserted key value. So that is why 49 came here and 51 is written here. Next we see 55. 55 is greater than 47, so it will go from root to right child of 47, and it will come here. So 50 is greater than 49 and less than 51. So this node is reaching the maximum limit of maximum number of key value. So we can split this into two child. So this 50 will go up to the root node. This root node will come here and it will be placed here. It's supposed to be here, but the maximum limit of this block is reached, so overflow will come. So this block also needs to be subdivided into two child. So this will form other new node. So 50 will be a higher node or root node. So left of 50 will be 55, here 55, and right of 50 will be 55, and left of 50 will be 37 and 47. So this will come here. 50 is a root node, and internal nodes will be 37 and 47, and right child 55 will be right of 50, and 50 and 51 will be left of 55, and all the values greater than or equal to will be right child of 55, as you see here. So we have three levels: level 0, level 1, and level 2. And we scan 58. 58 is greater than 50, and it is also greater than 55. And if we have a space here, it was previously 61, we can rearrange by ascending order. So 58 will be between 55 and 61, so 55 directly inserted in the first case. And last, we will scan 80. 80 is greater than 50, we'll go down here, and it is greater than 55, greater than 60, also we'll go down here. So but here 80 cannot be inserted directly here, so we'll split this value into two. So this 60 will go to this place, right to 55, because splitting node. So if after we split, we can get other more child, that is 3 child will have this right child of 50. So 61 and 80 will be new node, a new leaf node. So this 61 copy of 61 will be present or written here next to 51 as a root node. So final B tree is created by using these key values. Those are given key values based on the condition we created. And as we see here, all the values are sorted order, but here our values are not sorted because 55 is less than 61. Here we see 49 is also less than 55, 50 is also, so those values are not arranged in ascending order or in sorted order. But here all the leaf nodes containing all the key value also from 32, all the listed key values are written here at the leaf node, and all copies of the root node are present at the key also here at the leaf node. 37, 47 is here also, 37 is here, 50 is here, 55 is here, and 60 is here also. So that is right biased B plus 3 because the copy of the root node is present at the right child, including the right child. So all the values left to the root node is strictly less than the root key value. That is why it is right biased B plus 3. Now searching of B plus 3. So if you apply searching, we are starting from root node and getting deep to the leaf node, so that we have to take the height of B plus 3. So like if we search 53 from this B plus 3, so comparing 50, the root node with 50, so 53 is greater than root node 50, so we'll go to right child because it is given as right biased, so it is less than 55, so we'll come to left side, but left side we cannot get 53 here, so we'll return the key that 55 pointing to the data record is not found. So next 40 is less than 55, so we'll go left side of the tree and left child comparing the inner node, so 37, 45, 47, so it is between 47 and 37, so we'll go this direction. So we are getting this child right of 37 because it's greater than 37, so at the right of 37 we can get 40 here, so key value is found. So at the leaf node we are getting this key value. So in B plus 3 we have to start from the root node till the leaf nodes we are reaching, because the root node contain also the leaf node. Copy of the root node will be at the leaf node, so we have to go to deep to the root node while searching. So this is the height of B plus 3, so the time complexity will be held by this B plus 3. This is order of H will be direct linear search. If linear search, order of H will be linear search, but B plus 3 is not that case, so we're comparing from top to down and we're following the sorted linked list array, so it will be order of log n. Log n, we can say also k value, we can say sometimes k or n. N is the key value that are present in the node, leaf nodes and inner node. So, but those key values at the leaf node all pointing to the data should be present at the leaf node. So these are key values. Number of these key values will function as the time complexity of searching of key. So here is the algorithm what we taught already. So if we get the value, you can display. If we cannot get the value, you cannot display. So here is how you can search it binary tree key values. Here is deletion operation in B plus 3. So we'll delete these values from this given tree. So the condition of the previous, we have already the same condition as we see. And two main cases in compress, we can two main cases while deleting the B plus 3. One simple case will be if we have fulfilling this condition and we can have maximum number of children, like maximum number of key. For example, here minimum number of key, we can have one minimum number of key. If we can have 2 or 3 keys here, we can simply delete from the leaf node. So deleting starts from the leaf node and going up to the root node. So if we delete the leaf node and root node, if some values are present at the leaf node and root node, we have to merge, or we have to go for other condition by borrowing from the leaf nodes and getting some key values from the left child through the root node. That will happen while deleting. And we will see all those things in example. Here is algorithm. So the algorithm says that if we start from deleting, searching from the root node deep to the leaf node, if the leaf node is fulfilling the condition given, so minimum number of key is fulfilled, so extra that key can be deleted easily without disturbing all the B plus 3. Else if the sibling can lend a key or borrow the key, the deleted key will borrow from the sibling. So then after that we will adjust the link, and if else we can merge the children nodes. So the children nodes will have full number of key, so we can delete one of them, and if the keys are less number of child, so that can be borrowed from the next child or the sibling child. Or if the case cannot borrow from the siblings, so we have to go for merging of children. The next is the element if present is the internal node. So if the internal node present, we have to see 3 more cases. If the nodes have m by 2 ceiling of m by 2 children, delete the simply and replace with the minimum of right child. So one case present is the leaf node and also the inner node. So we can simply delete them and replace that place with minimum number of right child, because we are following right based p plus 3. If else the key value is less than the minimum key value, we can borrow from the sibling and adjust the parents or the inner nodes and child links. And otherwise, we can go for merging of the siblings. So now start from deleting 51. 51 it was here before, 51 it was here. We can delete simply here because 50 is already here. We can minimum of 1 key value in a block in each child. So 51 can be simply deleted. Example, that is case 1. 61. 61 is here. As you see, 61 is also present at the inner node. So if we want to delete this 61, simply delete here and set this value by 80, because this space cannot be free. So we can fill 80 on this place, and this place, this 61 place will be also filled by 80. That is why you can see here 80 is the minimum value of the right child, because the right biased tree will have minimum value 80. Other than you don't have any value, so 80 will be present here, 80 will be go up to here. So right biased b plus 3 minimum, right biased will go up and replace the deleted node. This is what we are doing here. Minimum value will go up and fill the deleted value. If we are going to delete the minimum, the left child, so maximum of left child will go and fill the deleted value. So these two cases will be seen. One is already done here. This next case will be seen next example. Delete 50. 50 is the root node here, first root node, and it is also present at the leaf node. So first we will delete here, and if we delete here, its value is a b plus 3. b plus 3 should have minimum of 1 key value for order of 4 in this given condition. So we have to borrow 55, and next node will be 55 and 58. So it will ask him, so if it borrows 55, yeah, it can borrow because it can have more than number of minimum key value. So this 55 will be borrowed by this, and this can be deleted, and these two will be merged, 55 and this empty block will be merged, and 55 will be filled here. Yeah, then 55 will go up here, and 55 also, 50 is deleted here. So if we delete 55, this 55 will go up and fill this place. So that is why 55 is taking the place of 50, and this deleted value, this removed value will contain 58. That is why the minimum value of right child will go take place the place of deleted value. So 55 place will be taken by 58. So another way, deleting 40, that is simple case. 40 is here, so you can delete because we have minimum number of 37 reserve, so you can simply delete 40. And deleting 37, 37 is here, so that's minimum number of key value. We cannot delete simply here, so we have to borrow a value from the sibling, like from here or from the left child. Now previously we borrowed from the right child, so that is borrowing from the right child means that deleting the deleted key value, targeted value, and merging the borrowed value, and also deleting the root node, so that will be replaced by the minimum number of right child. So now we can see example how we can borrow from the left child. So left child of 37 is 32 and 34. right child is 37, so 40 is already deleted here. 40 is already deleted. So this maximum of left child will be 34. 34 will be borrowed to 37 through the root node. Through the root node, it will take this root node and it will go down here, root node. So 37 will be deleted here. So this root node 34 will take this place, 37 place, root node, inner root node, and 34 will become here. So this empty value and this borrowed value will merge, and that we can have only 34 at this place, at this child. Now deleting 55. So 55 is at the root node and present at the leaf node. So 55 cannot be directly deleted because it's minimum number of key. So we will go for merging 58 and this space, deleted space of 55. So this will be merged together, and this 55, when we delete this 55, it will take the key value of minimum number of right child, that is 58, to go up and contain this space. So 58, and 80 will go and take this place. So 80, it came here. So left child of 80 will be 58 and right child of 80 will be 80. So it can be doing like that. Now delete 80, the last value. So 80 is here, 80 is here. So we cannot delete directly 80 from here because it's violating condition of b plus 3. That's minimum we can have one key at one child. So we cannot delete it simply directly from the leaf node. And it is also present at the root node, inner node. So we will borrow from the left child. Left child will be here. These all are left child. So from the left child we'll borrow maximum value. So maximum value will be maximum value from 34, and first node is 34 and 47. So 47 will be borrowed by through the root node. This root node will be substituted by 47, and this will go down here, and this 58 will come here, and 80 simply can be deleted here. So 80 will be deleted here also. So this place and this place will be merged. But here right side of 47 cannot be left child because we are following right bias. So this child 47 and 49 will go to the left child of 58 as the right side of 47. So here is a final format 3. So 47, 58, and left child of 58 and right child of 47 will be 47 and 49. So 58 is a root here, inner node. So 58 is present here. There is another important point that we can reduce the height using merging of nodes. So while we are deleting the key at the leaf or at the inner node that cannot borrow from the siblings, so we will go for merging of nodes. So in this case 32 cannot borrow from 34 because 34 already having minimum number of keys that cannot lend to 32, and that minimum number of key for order of m is equals to 4. 4 by 2 minus 1 will be minus 1, plus 1. So that is the minimum number of key that we have to have in each children. So only one children can present in each node, but empty node cannot, we cannot have an empty node. So in this case m order of b plus 3 was given for previously. So 4 by 2 minus 1 will be 1 child, so it cannot lend to this value. So if we delete 34 here, 34 also here, so we cannot left as this empty node. So also another condition, b plus 3 have a minimum of 2 children, so b plus 3 cannot have a single children, so we have to fulfill that condition also. So if we want to delete 34, we need to merge these two blocks. So this block will be removed, and because 34 will be deleted and 32 block will be left, and this block also be removed. So 58 here at the second level, 58 will go up to the root node because one level go up, and then the left child of 47 will be 32 and right child of 47 will be 47 and 49. This node will be removed, and right child of 58 will be 58 itself. So finally we can get this like B plus 3. So this B plus 3 height is reduced by one level, as we can see here. Some advantage of B plus 3, self-biasing data structure for executing accurate and faster searching of insertion, deletion on the data. So on the disk data, we are using insertion, we are operating insertion or adding some values or deleting some values or searching some pointers or values in the data that we have in our table. So this is very fast and accurate while we are using B plus 3 data structure. We can easily retrieve complete or partial data because of going through the linked list. So linked tree data structure will give us much easier and high performance because of that short time will give us getting all the dense data in the leaf node. So storage of data on the leaf nodes and subsequent branch of internal nodes evidently shortens the tree height. So storage of data on the leaf nodes and subsequent branch of the internal nodes evidently will shortens the tree height, and as well it consumes much less space on storage devices. So this is very some advantages of B plus 3. And disadvantage of B plus 3, B plus 3 is less efficient on static data table, static table. So B plus 3 is working on dynamic table. If we have data in a disk or in a table format or big data, for that we can use pointing this, accessing this all entries by using specific key that are found in the leaf of B plus 3. So that pointers can be this point, for example, this value, this entity value, entry value will be accessed by one key point in the B plus 3 that found in the leaf node. Also, we can have a disk data like this, a disk. So disk will be like this. So for the disk we'll have a track number and segment number. So that track number and segment number will be accessed, that will used for accessing the data in a disk. So if we want to this value this at this point, what is the entry at this region? So this region will be segment value and track number. Track number 1, for example, this round, and track number 2 will be this. So this segment and this segment number will be given. So using that we can access data from the disk also. So this is a dynamic operation. So B plus 3 also used for dynamic operation for a big data that is found in a big data management. Any search will end at the leaf node only because all the leaf nodes are, all the keys are present as a leaf node. So we are mainly searching for or going for key values that pointing to the data. So our key values are present at leaf node only. We cannot put our key values in the root node or inner nodes. Time complexity of B plus 3 will be log hn, log n base h. So n is a number of keys and h is the height of B plus 3. Waste of memory because of duplicated keys can be present at the leaf node and root node also. So that will not happen in B or balanced tree, but B plus 3, all the keys should be present in the leaf node. So we don't have any data or keys that point to the data records at the leaf node or inner nodes. That is why memory will be wasted because of duplicated value, as we were seeing there. So here 47 and 47 is here 58, 58. So duplicated value will give us wastage of memory. So here we see some comparison between B3 and B plus 3, because B plus 3 is extension of B3. So we can see some comparisons between what is the advancement of B plus 3 from B3. So space is the same, yeah, space is order of n. And while searching, we are using B3 of data, that is order of log n, because all some key values can be present at the root node itself, inner node itself. So we can also have at the leaf node also. But here all the key values are present as the leaf node. We have to go deep from the root to the inner node and then reach to the leaf node. So for that we are traversing one linear search called by linked list. So for that we are using is B here, and n is the key value of the index. So it is the same for all searching, insertion, and deleting. So it's a comparison table. Storage in B plus 3, search keys and data stored at internal or leaf node. So B plus 3 stored only in leaf node. Only keys are stored in leaf node, but here we can store in data can be stored in root node or inner node as well as leaf node. In 3 cases we can store the data, but here only leaf node can store the data. Data leaf nodes and trees store pointers to the records rather than actual record. So in B3 or balancer tree, root node and inner node can point to the data block or the children as well as pointer to the record. So that is very much possible in B3, but that is not possible in B plus 3. So all keys at the leaf node can only point to the records, not on the key values on the root and inner node can point to the records. So it is wastes some space, and it does not waste space. This is the difference between B plus 3 and B3 in some case. And here is a conclusion. These are some references I used. Thank you for watching. I was Jonas Alami from VIT. Thank you.